come back again. We're looking at unsupervised learning now. Algorithms. We have looked at some various supervised learning algorithms. So we want to look at some unsupervised learning algorithms. And like I explained in the intro section, that it's algorithm that does not require a supervisor. Okay, no target variable, no label required for supervised learning. Okay, so it's a type of machine learning that learn patterns and structures within the data without human supervision. Then it uses machine learning algorithm to analyze the data and discover underlying patterns within unlabeled data sets. So in this case now, the data are not labeled like the previous supervised learning where you have the labeled data, target variables. Okay, in this case, there's nothing like that. So the algorithm by itself automatically run the model and try to computerize the data and separate them into their different clusters. So in the training process, the algorithms learn and infer their own rules on the basis of the similarities, patterns, and differences of the data points. The algorithms learn without any label, that is to say, no target variables, target values, or pre-trained data. So we have the category of unsupervised learning. Okay, but they are broadly divided into three categories. So the first category is called clustering. Second one is called association. The third one is called dimensionality reduction. For clustering, that is used to group a set of objects or data points into clusters based on their similarities. You know, this is what they look alike. They are very similar. So the goal of this technique is to make sure that the data points within the same cluster or similarity should have more similarity than those in the other clusters. All right. So it's sometimes called supervised classification because it produces the same result as classification does, but without having predefined classes. All right. So in this case now you can see here we're trying to see, okay, this are all together raw data. So the model help us to process it here and help us separate the cluster to different categories. So this is what we call clustering. All right. Now there are different type of clustering. Okay, you have k-means clustering. This partition data into k spherical clusters by minimizing within cluster variance, which is called k-means. The k-means for speed. All right. So this is for speed. When it comes to this one is a speed base. It's very fast than other ones. That's what it means. So we have clustering, build a tree-like hierarchies of clusters using agglomerative bottom-up or divisive top-down approaches. We have what they call mean-shift clustering, discover clusters by iteratively shifting points toward the mode. This is called peak density of data distribution. We also have what they call agglomerative clustering, this bottom-up hierarchical method that merges similar cluster iteratively. We also have what they call db-scan clustering, groups these dense regions of points separated by sparse areas, identifying noise points. db-scan is basically for irregular shapes. Okay, when you have some shapes that are irregular, that is so we have HD B-scan. It's called an advanced version of db-scan that finds cluster of varying densities using hierarchical stability. We also have what they call batch clustering. This scales efficiently to large dataset by building up clustering feature. 3 for incremental clustering. So we have several types of clustering, and we also have what they call second part is called association approaches. So this is rule-based technique that is used to discover association between parameters in a large data set. It is particularly, or rather popularly used for market basket analysis, allows companies to make decisions and recommendations engines One of the main algorithm that is used for association rule mining is the a priori algorithm. So this association rule learning, which means that you can see the example here. 93% of people who purchase item A also purchase item B association. What you have inside here, you also have it here. What you have here, you also have it here. I mean, you have what you have here, you also have here. What you have here, also have it here. So that is called association. All right. What you have here, also have it here. All right. Association. That's what it means. So what you have in one place, you have in another place. All right. So we have different types of association. We have a priori association, which is a common one, which define data points that are frequently repeated and discover association rules within transactional data. So we also have what they call FT growth, uses a frequent pattern tree to mine rules without candidate generation. This one is faster than a priori. Okay, we also have for ECLAT, which employs vertical data format and intersection based search for a frequent item set. Also have what we call linear time closed set item set miner, which optimizes for finding closed frequent item set in linear time. Also have what we call recursive elimination, which recursively projects databases to discover frequent item sets. Also have what we call HMine, uses a hyper structure, the H means hyper there, to efficiently mine frequent patterns in large datasets. Also have what they call optimum pattern discovery for utility mining, which focuses on utility-based item set mining beyond frequency. We have top K rules, directly mines the top K most significant rules. These avoid minimum threshold tuning. We also have frequent item set mining with net trees. This leverages net tree structure for high-speed mining. Also have what they call KAMA, continuous association rule mining algorithm, process streaming data incrementally for real-time rule updates. So these are a lot of examples we have for associations, which are not commonly used most times anyway, but we are going to look at a few of them as we journey in this particular teaching. So we also have dimensionality reduction, which is very common, okay, which reduce which is a process of reducing the number of features or variables in the data set while retaining as much as of the original information as possible. In other words, it is a way of simplifying the data by reducing its complexity. Maybe you have a 3D structure, for example, of data or high-dimensional data. You want to reduce to the lower dimension data. So we have 3D down to 2D, down to linear base, which is 1D, one dimension. So it's commonly, one of the common methods is called PCA, Principal Common Analysis, which project data onto orthogonal axis of maximum variance. So that is the first one that we have there. So we have a PCA. So we also have what we call singular value decomposition, which linearly transform data into a lower dimension space by projecting it onto orthogonal axis, because singular vectors. For practical machine learning, most times we use what they call truncated SVD. This is found in Scikit-learn, or we use what they call randomized approximation for large data sets. So we also have what they call LDA, linear discriminant analysis, which is supervised but often grouped here, maximizes class separability, which requires labels. This one requires labels because most of this one is only used for a classification algorithm. Most times I've used it many times in the publications for classification algorithm, and they work perfectly well. We also have non-negative matrix factorization. So this one decomposes data into non-negative components for interpretable features. And we also have for factor analysis, which models observed variables as linear combination of latent factor plus noise. So this is a linear base. These are linear base, okay? Linear base. Also, called non-linear base, such as TSN, distributed stochastic neighbor embedding, preserve local similarity for visualization, 2D or 3D. We have a UMAP anyway, uniform manifold approximation and projection, balances local and global structure faster than TSNA. We also have autoencoders for neural networks, learn compressed representation via encoder and decoder networks. We have what they call kernel PCA, which extends PCA to a non-linear data using kernel tricks. We also have what they call isomap, they preserved geodesic distances on manifolds, e.g., switch rule. We also have what they call locally linear embedding models that which model data as linear patches in low dimensions. The third part is called sparse method. The sparse method, we have don't forget, we have linear, we have nonlinear, we have sparse. One of the examples is called sparse PCA, which had sparsity constraint to PCA for interpretability. We have what they call dictionary learning, which represent data as sparse combination of dictionary atoms. We also have what we call specialized techniques apart from the sparse. One of them is called random projection, which uses random matrices for ultra fast approximation. We also have independent component analysis, which separates mixed signal into independent sources. E.g., for audio, we have what they call Laplacian eigenmaps, focusing on preserving neighborhood relationship. So these are the three structures we have, both clustering, association, and dimensionality reduction. We also have advantages of each of them now. When you unsupervised learning, rather, no labeled data required, which I have explained before, no target variables. Unsupervised learning doesn't, apart from LDA that has, LDA actually have label, yes, though it could be used as a unsupervised learning, at the same time can be used as supervised learning. I mean, for classification, at the same time, can also use as a unsupervised also. So we have this one does not require label. We also have discovering high patterns. It discovers high pattern. It helps in recognizing pattern and relationship in large data sets, which can lead to gaining insight and efficient decision making. It is suitable for complex tasks. It is efficiently used for various complex tasks like clustering, anomaly detection, and dimensionality reduction. The other side of it is that it is difficult to evaluate. Without labeled data and defined targets, it would be difficult to evaluate the performance of unsupervised learning algorithms. Most times, also inaccurate outcomes can be frustrating. The outcome of an unsupervised learning algorithm might be less accurate, especially if the input data has noise, and also since the data is not labeled, the algorithm do not know the exact output. So this is what you have briefly under unsupervised learning. So this is just a general overview of unsupervised learning. So later we are going to be looking at some of the algorithm one by one. I mean, so few of them, not all of them, few of them. Just look some a few of them on under each category, and we proceed further. So thank you for listening today. I will see us in the next class. I will look at each of the algorithm one by one. Thank you so much.